Hello everyone, I'm Anurag from Srinivas Raman Institute of Technology and from second BTech in Computer Science and Engineering, the specialization of Artificial Intelligence and Machine Learning. And my subject name is Discrete Mathematics and Graph Theory, and the subject code is 23MAT07, and my bearing roll number is 23401357, and my topic is find the generating functions of the sequence 0, 1, minus 2, 3, minus 4. And these are the definition for the generating functions. In discrete mathematics, a generating function is the formal structure that represents a sequence of numbers as a power series. For a sequence a0, a1, and so on, and the generating function f of x is the series. F of x is equals to a0 plus a1 x plus and so on plus an x power n plus is equals to and so on is equals to summation I is equals to 0 to infinity ai into x power I. There are various types of generating functions including ordinary generating functions, exponential generating functions, Lambert series, Bell series and Dirac series, and these are the types of the series here we can see in the generating functions. And here the sum of some points of the generating functions. Generating functions allow us to manipulate the sequences as a single entity with the goal of understanding it better. Generating function is a method to solve the recurrence relation. Generating functions can be used for the following purposes: for providing some of the combinatorial identities, for finding asymptotic formulae for terms of sequences. And the main reason for the using generating function is to solve the recurrence problems and recurrence relations. It can be used to solve various kinds of counting problems easily. It can be used to solve recurrence relations by translating the relation in terms of sequences to a problem about functions. In simple words, generating functions can be used to translate problems about sequences to problems about curve functions which are comparatively easy to solve. A generating function is a tool to discrete mathematics to represent a sequence of numbers as a power series. Examples of generating function. Here we can see some examples in our generating functions. First example, 1, 2, 3, 4, 5 and so on. The generating function is 1 by this. For this, the generating function is 1 by 1 plus minus 1 by 1 minus x whole square. And the second example is 1, 3, 5, 7, 9. And for this, the generating function is 1 by 1 minus x plus 2x by 1 minus x whole square. 1, 3, 7, 15, 31, 63 and so on. The generating function for this is 1 by 1 minus 3x plus 2x square. A generating function is just a number way of writing a sequence of numbers. Here we will be dealing mainly with the sequence of numbers which represents the number of problems of size n for an enumeration problems. The interest of this notation is that certain natural operations on generating functions lead to the powerful method for dealing with recurrence generating functions, and these are the some of the points and examples for the generating function. Let a0, a1, a2 be and so on be a sequence of real numbers. The function f of x is equals to a0 plus a1x plus a2x square plus and so on is equals to summation I is equals to 0 to infinity ai into x power I is called the generating function for the given sequence. Examples: sequence c into n comma 0, c into n minus n comma 1, and c into n comma 2 and so on, c into n comma n and so on. For this generating function is 1 plus x whole power n sequence 1 comma 1 comma 1 and so on, 1 comma 0, the first n plus 1 terms of n generating one generating function. And for this, the generating function is 1 minus x n plus 1 by 1 minus x. 1 minus x n plus 1 is equals to 1 minus x into 1 plus x square plus and so on plus x power n. Sequences 1 comma 1 comma 1 and so on. For this, the generating function is 1 by 1 minus x into modulus of x is less than 1. And this is the main topic of us. And to find the generating function of the sequence 0 comma 1 comma minus 2 comma 3 comma minus 4, we wanted to express the sequence in the form of a power series. G of x is equals to summation n is equals to 0 to infinity a power into n power n, where a power n is the nth term of the sequence. The sequence given is a0 is equals to 0, a1 is equals to 1, a2 is equals to minus 2, a3 is equals to 3, a4 is equals to minus 4 and so on. It a power n is equals to appears that the sequence allows the pattern an is equals to minus 1 power n plus 1 into n. This can be verified by noting that for n is equals to 0, a0 is equals to minus 1 power 0 plus 1 into 0 is equals to 0. For n is equals to 1, a1 is equals to minus 1 power n 1 plus 1 into 1 is equals to 1. For n is equals to 2, a2 is equals to minus 1 power 2 plus 1 into 2 is equals to minus 2. For n is equals to 3, a3 is equals to minus 1 power 3 plus 1 into 3 is equals to 3. For n is equals to 4, a4 is equals to minus 1 power 4 plus 1 into 4 is equals to minus 4. Thus the generating terms of the sequences is an is equals to minus 1 power n plus 1 into n, and this is the formula for this. Generating function. To find the generating function g of x for the sequence, we will consider g of x is equals to summation n is equals to 0 to infinity an into x power n is equals to summation n is equals to 0 to infinity minus 1 power n plus 1 into n into x power n. You can separate out the term. First term a0 is equals to 0, so we will start the sum from n is equals to 1. G of x is equals to summation n is equals to 1 to infinity minus 1 power n plus 1 into n into x power 1. Now we can find a closed form for this sum. There is a known result that the generating function for the sequence 0, 1, minus 2, 3, minus 4 is g of x is equals to x by 1 plus x whole square. Thus the generating function for the sequence 0, 1, minus 2, 3, minus 4 is g of x is equals to x by 1 plus x whole square. Thus the solution for the generating function for the sequence of 0, 1, minus 2, minus 3, minus 1, g of x is equals to x by 1 plus x whole square is the solution for this problem. Thank you for your attention and thank you for listening.